Here's a few more spectra with some other splitting patterns to be aware of. This is 2-chloropropane here, or isopropyl chloride. And isopropyl groups show up a lot in chemistry, and they have characteristic patterns in their NMR spectra. So you can see the pink hydrogens, those 6 give rise to one signal here, even though it's split into actually 2 peaks. And then the blue hydrogen is going to give its own chemical shift, and even though it's a very small signal because it is just due to the one hydrogen, there is a lot of splitting going on. Kind of hard to see looking at this. You can tell it's not a simple singlet, but it is expanded here to emphasize that it is a septet. We do have 7 peaks. The ones on the edges are very tiny, but that is 1, 2, 3, 4, 5, 6, 7 there. And that is split because there are 6 hydrogens on the adjacent carbons. And when you have splitting into a septet, that usually means you are being split by 2 equivalent methyl groups. And that's really what we have here with isopropyl. In the meantime, those pink hydrogens here, the ones that are highlighted that way, the 6 hydrogen, this is a doublet. Sometimes you see a little D for doublet. And again, very close together, kind of hard to see, so that is expanded here. I guess you can see the doublet more clearly in that expansion. And that doublet is because that signal is being split by a single neighboring hydrogen. And that's what is true for the 2 methyl groups. On the carbon that they are connected to here in the middle, there is that single hydrogen. And so just as with ethyl groups, we have a triplet and quartet pattern. With isopropyl groups, we get a doublet and septet pattern for those. Here's another example of some splitting going on here. We've got a CH hydrogen and then methyl hydrogens here. This is 1,1-dichloroethane. So a fairly simple molecule and a fairly simple spectrum as well. Just 2 peaks, or 2 sets of peaks, I guess I should say. One of which here corresponds to a quartet. And so there's the expansion of that, and again this larger signal's a doublet. So sometimes you see them labeled D for doublet, Q for quartet here. And again, quartets arise because they're being split by 3 neighboring hydrogens, and methyl groups oftentimes give rise to quartets for the hydrogens on an adjacent carbon. And meanwhile, just as we saw with the isopropyl example, when you have a single hydrogen that is coupled to neighboring hydrogens, they give rise to doublets. So this, for example, is a nice way to distinguish this 1,1-dichloroethane from its isomer. If we had the chlorines on adjacent carbons, here's the isomer of the 1,1-dichloroethane, 1,2-dichloroethane. And in this case, by the way, all 4 of those hydrogens would be equivalent. On both CH2s, they're attached to another CH2 that has its own chlorine, and there's the direct attachment to the chlorine that's just below. So there's no splitting here because you only get splitting between sets of non-equivalent hydrogens. And the symmetry of this molecule makes it just give rise to one single peak. Certainly very different from what we see here with its 1,1-dichloroisomer. So telling apart isomers is a thing that NMR is very good at doing. A little bit more signal splitting here, including an example of a pentet, a set of 5 peaks. You can see over here it's labeled as a pentet just to make sure that we can count 1, 2, 3, 4, 5. That means that that signal, that group of peaks, is due to the fact that there are 4 adjacent equivalent hydrogens. Now you can't have 4 hydrogens on one carbon in any of these examples, but the pentet here would kind of, I'll just draw it over, it's going to go along with the CH2 hydrogens right in the middle there, because notice there's CH2 groups on either side. They are non-equivalent CH2 groups. One has these, this is a carboxyl group here, the other one has this benzene ring, But those 4 hydrogens will cause a splitting of the hydrogens right in the middle to split into 5 peaks. So 4 plus 1 is 5, and that's how you come up with a pentet. These others are triplets, little t for triplet. And it's kind of hard to know which triplet goes with which CH2 group. They're obviously very close in chemical shift, but it does make sense that in addition to this pentet, we would get 2 triplets. These CH2 hydrogens, well, there's a carbon over here in the ring, but it does not have any hydrogens on it, so nothing to split that CH2 peak. And this is next to a carbonyl, which has 0 hydrogens, so there shouldn't be any splitting on that side. So they're just, both of these CH2s on the edges here are split by the CH2 in the middle, so they give rise to triplets. And then finally, having our carboxylic acid hydrogen in the structure means we expect a peak way over here around 12 parts per million. That right away tells us we have a carboxylic acid. And then finally, what's left is the hydrogens that are implied to be on this ring. And with a benzene ring, that means if you don't have anything else substituting off, we assume we have hydrogens. Those 5 hydrogens are giving rise to this jumbled peak here. That's not really a simple splitting pattern, but it is a cluster of very closely spaced peaks that are all around 7.3 or so, right in the range we would expect for the hydrogens on a benzene ring. So this structure does correlate with all of the peaks in that spectrum, and there are no peaks for which we cannot make sense of. And notice again, this over here at 0.0 is our TMS. That's just our standard, and otherwise there's no peaks that are showing up that we can't associate with hydrogens in the molecule we have there.